Hi everybody, and welcome to part 3 of exercise 1. And again, in this problem, we are trying to determine bases for eigenspaces and to answer the question as to whether this matrix is diagonalizable or not. Okay, so we will start with part A here, which means we're looking for eigenvalues. So let's write out what the determinant of A minus lambda I would look like. Okay, and notice that kind of the same thing happens here as what happened with matrix 2 in the last video. This would be really ugly to expand by hand. We don't have any zeros in this matrix, and so there would be a lot of algebra involved. And so here's where I really recommend going to technology. Okay, have Wolfram Alpha or Mathematica or your calculator, if it can do that, figure out what this determinant is for you, or at least to do the factoring for you. Okay, if you do that, this actually winds up coming down to a nice simple factorization of negative lambda plus 2 cubed. Okay, so it's kind of interesting. You set this equal to 0. There's actually just one eigenvalue. It's repeated 3 times in this case. All right, and so we've just got one eigenvalue to check for eigenvectors. So let's take a look at what happens if we do that. So we substitute lambda equals negative 2 into our A minus lambda I matrix. We are going to get negative 2, negative 1, 3, negative 2, negative 1, 3 again. Okay, and negative 2, negative 1, 3 again. Interesting matrix there. We've got the same row 3 times. So you can kind of see what's going to happen here. Then if we do reduction, we're going to get 2 rows of zeros. Okay, which means 2 free variables, just one pivot position sitting up there in the upper left-hand corner. So let's see, if we make x2t and x3u, okay, you can confirm my algebra. If you take that and solve it for x1, you're going to get 1/2 times negative t plus 3u. Okay, so since we've got 2 free variables, that tells us that the dimension of our eigenspace should be 2. All right, so let's go through kind of the standard algorithm for producing 2 linearly independent eigenvectors here. One thing we might notice is that because of this 1/2 here, it's convenient to make our non-zero free variable equal to a multiple of 2. Okay, so to generate the first eigenvector, I'm going to choose t equals 2 and u equals 0. Okay, and if we do that, that's going to lead us to a first eigenvector of negative 1, 2, 0. Okay, and flip that around, make t equals 0 and u equals 2. That's going to lead us to an eigenvector that looks like 3, 0, 2. Okay, so to finish part A, we just need to make our table, see what our basis for our eigenspaces are. And in this case, there's only one eigenspace. Okay, so if lambda is negative 2, that's our only eigenvalue, we discovered that we're going to get 2 linearly independent eigenvectors. Okay, and there's a basis for our one and only eigenspace in this case. Okay, so what about part B then? This is asking us about diagonalizability. Okay, is this a diagonalizable matrix that we started with? Okay, well, we can answer that question by looking at the multiplicities again. So the multiplicity of our eigenvalue is 3, but notice we only got 2, our eigenspace only had 2 vectors in it. Okay, so the fact that the number of vectors in our basis is less than that multiplicity tells us that our matrix is actually not diagonalizable this time. All right, so let's see if we can put that into words here. So the multiplicity of lambda 1 equals negative 2 is 3. But the dimension is 2. Okay, and that tells us that our matrix is not diagonalizable.